So we started discussing gravitational waves and full general relativity, and what we saw last time was that we got the universal structure as Scri, and that is common to all space-time, so that does not have any information about gravitational waves. But there's a next order structure which does, and that next order structure is the derivative operator. And we saw that because Scri is a null-free manifold, and we're working in the divergence-free frame. Because of this, mathematically, that null surface has the same properties as a non-expanding horizon and even a weakly isolated horizon. It's not a physically weakly isolated horizon because its properties are with respect to the conformally rescaled metric and not the physical metric. But because of that, the statement that we saw last time was that on Scri we have a naturally induced derivative operator. So this is the this is the part F that we're talking about, which is radiative modes. And we saw that we have got the universal structure of these pairs. And Scri is null, is a null, so this metric is degenerate, etc. And this is common to all space-time, but also in the divergence-free conformal frame. Scri together with the metric and the exchange curve and the normal up here is mathematically is a shear-free, expansion-free surface and also geodesic, NA is a geodesic vector field. So mathematically in particular, it is a weakly isolated horizon. And therefore, that means that the weakly isolated horizon structure, there's a mathematical structure of a weakly isolated horizon. And therefore, the statement is that we have the space-time derivative operator, which kills the conformally rescaled metric. So Grad induces a correction D on Scri. And this D we saw last time, I mean, just because of the properties of Grad, it interacts very well with the universal structure, namely in any conformal frame, I got GAB that and a graph that gives me a derivative operator in any conformal frame, and in that conformal frame, DA annihilates the metric and DA annihilates also the normal to Scri. And therefore, the action of D is rather restricted, and last time we saw that this implies that in fact, so we got Scri like that, and I got a base space S. These are the integral curves of the null vector field. This is topology S2. I got a projection mapping from the integral curves of the null vector fields, the NA vector field, to the base space up here. I got S2 mapping up here. And then the statement is that that in fact, roughly speaking, because of these properties, for the covectors which are pulled back, the action of dA is completely determined because it is because of the base space. I got a non-degenerate metric Q bar AB, and I got a derivative operator, which actually is completely determined, and it knows how to operate on covectors here. Let's call it KA, a covector KA. So if I have KA bar, and if I pull this covector back to covector KA, it satisfies this condition and ln of K equal to 0. If I just pull it back. So already I know how d bar operates on it, so I can just pull back the action and I get the same action here. And we saw that just last time explicitly, that the action of D on so if you like these KAs which are tangent to these two spheres, like which are linear combinations of M and M bar, the action of D on on K such that K in A equal to 0 is determined. We don't have any freedom here. All the derivative operators, whatever we have, its action on these vectors is determined because it kills the metric up here. And the statement is that what is not determined is that the A is determined then by giving the action D and B, action on covectors L's, which are that, for which LA in A is not equal to 0, so we might as well just take LA in A is equal to -1. We can put anything here which is not equal to 0. The simplest thing is to just choose -1. So if I know the action on these covectors, then I know the derivative completely. So there's a universal structure, but what is different from one spacetime to another, from a stationary spacetime to a radiative spacetime, etc., is this derivative operator, which is induced in any conformal completion by the spacetime derivative operator. We've got a derivative operator D up here. But however, again, no matter which spacetime you have, the action of this derivative operator on these covectors is universal, and therefore the only freedom I got is this. So we're trying to answer the question, how many derivative operators do we have? And that is what now we're going to answer. Okay. Are there any questions? This is where we were. Are there any questions? So now we want to know how many such derivative operators are here. So because how many? How many derivative operators does Cry admit admitting satisfying these conditions? That's the question that we would like to ask, because that's the next rich structure. So if I take all possible space times, I complete them, I put the structure, the derivative operator on Cry. How many are there? Right? There are many. So how many are there? Well, so I can take dA minus d prime A minus dA, two derivative operators, operate on any vector omega A, say, and covector omega B, and that is going to be, of course, of the type C, A, B, C, omega C. This is, maybe I should not call it omega, let me give it some other name. Alpha. Alpha B, alpha C. Because little omega sometimes we use it, the conformal factor, so we not use that. So we got this. So there's given any two connections, the difference between them is a tensor, and that tensor is CABC. These connections are torsion free, so CABC just satisfies that it is symmetric. Now, if I just take this property that on K's, which are such that K dot n is equal to 0, then in fact the derivative operator is universal. So if I take now K such that K dot n equal to 0, there's a covector. And again, all these equations are on Scry, therefore I'm not putting hat on all equations. Every equation, if you like, has a hat. Then I must get here d prime A minus dA operating with AB. They all agree, so this must be equal to 0. But this, of course, is just equal to CABC times KC. That means if you give me any K, which is transverse to n, so it is in the two sphere directions, if you like, d by d theta, d by d phi directions, then in fact the derivative operators agree. Therefore, the contraction of CABC with something like this is always 0. That just implies immediately that CABC has the form some tensor sigma AB times NC. Because the only thing that will kill every covector which is perpendicular to n is n. Not very profound. So therefore, this must have the form sigma ABC times NC, where sigma AB is now symmetric up here. But we also know that dA of NB equal to 0. So that would immediately imply, again, this is true, dA, d prime A minus dA of NB is 0, because d of NB is equal to 0, d prime NB equal to 0. So this is also equal to 0. and this is just equal to CABC times ND, so it is minus CABC times NC. This is a co-vector, this is a contravector, that's why there is a minus sign. And the indices are the only way that you can write down. N is up, B is an upstairs index, and A is a downstairs index, and then we've got a contraction up here. So we know that this is equal to 0, so this is just equal to sigma AB times sigma AC times MC times, so sigma AC times NC times NB. So I'm just substituting for CABC from here. The indices are slightly different, but that's what we get. And so therefore immediately we find that sigma is transverse to N, sigma AB equal to 0. So how many derivative operators are there? Well, there are as many derivative operators as there are symmetric second rank tensors transverse to M up here. So as many D's as sigma AB, where sigma AB is symmetric and is transverse to M. So I got a 3-manifold. This just says that sigma AB, if you like, has components only along M and M bar. It's only the other, it's transverse components. And therefore, there really is a 2-dimensional tensor. No, not a 3-dimensional tensor because it's transverse up here. Or if you like, sigma is a symmetric tensor field. And this transversality condition kills 3 of the components. And therefore, I'm just left with 3 components. So therefore, this is 3 components. We can freely specify 3 components. And we use all the equations. This way used directly. And this equation dAQBC equal to 0 is automatically implied by the fact that that d minus d prime operating in k is equal to 0 if k is of this type, because q is of course of this type. Therefore, they all agree on q. So we use all the equations, and the statement is that we are left with this kind of 3 free functions of on Scra that you can specify. However, there's a catch, and this is a subtle catch, but it's more or less obvious that what we have up here in physical space-time is really a conformal metric GAB, which then induced QAB and A. So what happens under conformal transformations? Well, in general, of course, Q changes and N also changes. Q changes and N also changes up here in general under conformal transformation. But what happens if in fact I choose omega to be such that it is not equal to 1 in the interior, but on Scra it is equal to 1. So supposing I make a conformal transformation, GAB goes to G prime, or maybe G bar AB. Let me just make the notation because I think prime and bars are used in, yeah. This D prime AB was just any old derivative operator, so let me not use prime up here. So G bar AB, and supposing this is equal to omega squared and GAB, and supposing omega is of course always smooth, and in general, because we're a conformal frame, in a divergence-free conformal frame, ln omega is 0, it's only a function of theta and phi. But suppose that in fact omega is equal to 1 on Scra. I'm putting this hat now here because this is a space-time equation, and this is the equation just on Scra. So anytime there is a need, I will put the hat. If there's no need, I will not put hat. So up to here, there was no need. So if you like every equation is a hat up here, I just didn't put it. But now I'm intermingling what is happening in space-time with what is happening at Scra. Therefore, I put this omega equal to 1. So if I just do this, then of course, Q bar AB is equal to omega squared times QAB. It's just QAB and NA, N bar AB, N bar A, omega is equal to NA. So in that case, this frame doesn't change. But does the derivative operator change? First, one's reaction would be no, the derivative operator would not change because the frame didn't change. But that would be correct if in fact the derivative operator was completely determined by this metric and the extrinsic curvature. But it's not. There are infinitely many derivative operators up here, which means that if omega is equal to 1 on Scra, but its derivative of Scra is not equal to 1, then the metric and the null normal don't know anything about it, but the derivative operator, which probes one order deeper, knows about it. So under this transformation, what happens to grad prime A? So grad A. So grad A will go to grad prime. Will go to grad bar A. Okay, so grad A of GBC equals 0. Grad bar A of G bar BC equals 0. These are the two torsion-free derivative operators related to each other. And you can easily check what the conformal transformation property is. And the only thing that you have to always remember is the sign. Yeah. So the statement is that grad bar A minus grad A of any vector alpha. Again, this is in space-time now. This is in space-time. So this any vector alpha up here. So you work out the transformation, conformal transformation property. We have seen that a few times before. It's also, for example, in the appendix in Wall's book, if they make a conformal transformation of the metric, how the derivative operator changes, how the curvature tensor changes, and so on. And so that therefore I just get here minus, so this is equal to CABC, alpha C, and this CABC is just equal to minus omega to the minus 1 times delta AC, grad B omega. So it's symmetric in A and B, so therefore I just symmetrize here, put a 2, and minus grad C omega times G. So if I just make a conformal transformation, the derivative operator changes, and it changes by this particular formula. And therefore, if I take CABC times alpha C, in general, I will obtain this times alpha C up here. What I'm interested in is what happens to d bar A minus d A operating on alpha B. This is what I'm interested in. Where alpha B is now just within scribe. So supposing I just take the pullback of all this thing to scribe. Therefore, I'm taking. So this is what I would like to know. So this of course equal to d bar A. Sorry. This is grad bar A minus grad A alpha B. I pull back up this equation to scribe. Then grad bar pullback will give me some d bar. Grad pullback will give me d. And then I will get pullback of alpha B. This is what I'll get. So here alpha is in space-time, and that is why the ones on scribe will be pulled back. But this is exactly what we saw. So we can just find out what that is. So that it is this. So that will be equal to omega to the minus 1 times twice delta AC grad B of omega. And this is pulled back to scribe on indices A and B. This is pulled back to scribe indices A and B minus grad C omega times alpha C times GAB pulled back to omega. So I've just taken here, sorry. I've taken alpha C inside. So this operating on alpha is going to be equal to alpha is pulled back, and then I got this thing, and then here the indices A and B are pulled back, and I'll obtain. So I don't have to pull back alpha. Well, we're just pulling back the indices A and B. We're just pulling back the indices A and B. Okay. So this is what it is, right? The difference between the two derivative operators is equal to this. But we just looked at the possibility in which omega is equal to 1 on scribe. So if omega is equal to 1 on scribe, then of course this is just 1. This is a derivative operator operating on omega, and I'm pulling back to scribe. So this is just the derivative of omega within scribe, but omega is constant on scribe. Therefore, this is equal to 0, and I'm just left with this term. Therefore, this term is just going to be equal to. So there was a minus sign that I missed here. Minus omega minus 1. So this minus sign and this minus sign becomes plus, and then I get here just alpha C times grad C of omega times. So what we find is that in this case, this tensor CABC, if you like, has some very specific form operating on any alpha, it is of the type, what I get is really something which is proportional to the metric up here. But now the point is that if omega is equal to 1 on scri, that immediately implies that if I take in the physical space-time, so I should again be careful. So this is equal to, pull back up this is equal to that also. I should put hats. These equations are all hats up here. So omega is equal to 1 on scri. That means that grad omega is proportional to n. Because if I take a function which is constant on scri, and it's any function inside, and I take its gradient, that gradient should be normal to scri, because omega on scri, is it okay or is it not okay? I'm given a submanifold, I'm given a function which happens to be constant on scri but not constant inside. And the submanifold is actually constant. Therefore, its gradient should be proportional normal to scri. Right? Given any function which is constant on the submanifold, its gradient is always normal to the submanifold. And therefore, this is proportional to n. So therefore, we find this to be equal to some function f times alpha c and c. So if I just put in this language, we just find here that dA minus dB of alpha, dA minus dB, d bar A minus dA of alpha B, and any alpha which is put back to scri up here, this quantity is equal to in general sigma CABC times alpha C, and therefore that is of the type sigma AB times NC times alpha C. And this, what we are seeing is that this is of the type, so this is of the type F times alpha C and C times, there's no pull back, sorry. It's just alpha C and C times QAB. So what we find is that means that sigma AB in this case is just F times a metric. So this is a short calculation which addresses the following problem, or following issue. The issue is that I can have conformal transformations in the physical space-time under which the space-time metric changes. But the relative conformal factor little omega that we have could be equal to 1 at scri. It's not 1 everywhere. Its derivative of scri is not equal to 1, but just happens to be 1 at scri. If so, then it does not change the conformal metric and the normal to scri. But in the physical space-time, it still changes the derivative operator, because it doesn't change the metric here, but the derivative operator knows also what the metric is doing off scri, therefore it changes the derivative operator. And it changes the derivative operator by the formula that we wrote down. But because omega is equal to 1 on scri, in fact, the derivative operator changed. This term is the only one that survives. It's proportional to the GAB metric. If I pull it back to scri, therefore the two derivative operators differ from each other by sigma times NC alpha C, where sigma AB is just equal to some function times QAB. So what we had seen before was that given any two derivative operators, they differ from each other by the sigma AB, which has three components. Now what we notice is that the trace of the sigma AB is pure gauge, because say Javier has a conformal completion, and he finds his dA, and is perfectly fine up here. And then Jesus finds another conformal completion, but they all agree at scri, omega is equal to 1, but he will obtain a different derivative operator, and the two will differ by this formula, d prime minus dA is equal to sigma AB, sigma AC and C times, CABC times NC, or sigma AC times C. They will differ by the sigma AB term, and that sigma AB term is just a symmetric term here in general. But in this particular case, they will find the sigma AB just proportional to the metric. That means I can change sigma AB by making a gauge term, by making a conformal transformation. And conformal transformations don't have information about the physical metric, because physical metric has not changed. Its description in terms of the conformal completion has changed. Under that conformal transformation, the statement is that this sigma AB changes, and therefore that is gauge. So the sigma AB does characterize the difference between any two derivative operators, but part of the sigma AB is just fluff, it's gauge, it's just mathematical thing that happens because one chose one conformal completion and another person chose another conformal completion. So the statement up here is that the trace part of sigma is pure gauge. So the trace-free part is where the gauge invariant information is. So we're saying that the trace-free part. So I take sigma AB, and I can take the trace QAB, and this quantity is really going to be F here, or half F. So this will be equal to 1/2 F, because if I take sigma AB times QAB, sigma AB equal to that, QAB will be equal to 2 because it's a two-dimensional metric, and therefore this is pure gauge. Note that QAB, you have some freedom. QAB could go to QAB plus some VA and B, TA and B, where TA is any vector tangential to sky. But this condition, it doesn't change because sigma is already transversal to N. So I can choose any inverse here, doesn't matter which inverse I choose. So its trace can be taken with respect to any inverse metric, and the statement is that is pure gauge. So the gauge invariant part if you like, we can just call it equivalence classes of metric. D is up here. These are the D's. D is equivalent to D prime if sigma AB, which relates them, is equal to F times is proportional to the metric. So the gauge invariant part of these equivalence classes of connections, this is actually, it turns out that this encodes. So how many components does this have? So if I take now D bar minus D, so this I can change take the difference between the equivalence classes. Difference between individual D's was characterized by sigma. Therefore, the difference between the equivalence classes is characterized by trace-free part of sigma. So sigma AB minus 1/2 QAB times sigma CD. This is the trace-free part. And let us call the trace-free part. This is the trace-free part of sigma. Let us call it this little sigma AB. So the gauge, I mean, how many derivative operators are there? Well, there really is as many as there are 3 functions on scribe, because the sigma AB has 3 components, but one of them is gauge. So how many gauge invariant degrees of freedom are there in the derivative operator? How many connections are there which are sort of not contaminated by just trivial conformal rescalings with omega equal to 1 on scribe? The answer is that it is really the trace-free part up here, and because I have removed trace, this has 2 components. And these are the radiative modes of the gravitational field. We'll see a little bit more detail, but when you see these LIGO plots and all those waveforms, what they're plotting is the component of the sigma. So I'll explain in a minute a little bit more exactly what they're plotting. So these are these 2 components up here. So in other words, you've got 2 binary black holes which are radiating, which are rotating around, and they collapse and they merge. They form a single binary black hole. Then they send out some ripples in the space-time curvature. Then what changes at scry is the derivative operator. The metric does not change, the non-normal does not change, but the derivative operator changes. And that change in the derivative operator, sort of the physical part, the gauge invariant part, is contained in this sigma. And it is this sigma that registers the gravitational waves, and that is what is plotted in the plots, in the LIGO papers. Okay, so a little bit more. So what properties does sigma AB have? Let me write down again. Sigma AB, big sigma AB was transverse. The little sigma AB is big sigma AB plus something times the metric. The metric is also killed by n. Therefore, big sigma AB, little sigma AB is also transverse. Of course, by construction, sigma AB is symmetric, and it is trace-free. So it is transverse to N, the non-normal to N, it is symmetric, and it is trace-free. So this is called the transverse, symmetric transverse trace-free. You know, these modes are the modes of, these are the two modes, two radiative modes. Of the gravitational field. In full general relativity in the asymptotically flat context that we're studying up here. So this is the thing that I want to sort of emphasize now, and now we want to understand the properties of this thing called sigma up here. Are there any questions about this? That there are exactly two invariant quantities that I extracted out of the derivative operator. And the rest I just told you, we're going to see why all this is true, right? This is fine, but why these are the radiative modes, that's what we're now going to see. Is this your question?
Good.
No.
I think we started with choosing first a divergence-free conformal frame, and then everything else is in that frame. Right?
Yeah, everything is in that.
So should we not, have you not chosen that divergence-free frame, could we still recover basically?
Right, because the statement is that if you like, it is like partial fixing the conformal freedom. If I kept the full conformal freedom, then there's more, you'll get more components here. So this equation would not be just simple like that, but then there's more gauge and more equations, and we're killing some gauge early on because in some sense it is irrelevant, it doesn't matter. I mean, it's a matter of convenience, it's not, and we're going to, in fact, as we did last time, in order to talk about translations and so on, we can further fix the conformal freedom if we want, just to simplify mathematics. Not because it is necessary, you can do it without that. But the divergence-free conformal frame is something that really does cut the clutter a lot. If you remove that condition, there are just all kinds of extra terms which don't carry any physics, which you have to keep everywhere. Okay.
Sorry.
Yeah.
Those two modes take this form, let's say, in a particular gauge, or?
No. So this, I mean, other than in space-time language, in a particular.
Is this the kind of thinking to the linearized theory when one
we're going
to the TT gauge, the transverse?
So we're going to see the connection with linearized theory, because the way that I organize this course was purposely like this. Namely, most students have taken the first course in general relativity, so they have seen linearized gravity, so they're already familiar with it. So I didn't want to start with that, but rather I wanted to show the exact theory and then take its linearization so that they can see that that is really the same as what is happening up here. And then we're going to talk about the transverse traceless gauge in the linearized theory, how it is related, and that is what we're going to do just now. But at the moment, the statement is from the space-time point of view, I've not fixed any gauge, except by being on scribe. So I'm not saying that I mean, if you like, I'm assuming that the metric is such that it has sufficient smoothness on scribe, that it satisfies the boundary conditions we wrote down. And then there was it's not like this space-time transverse traceless gauge, but there's a conformal freedom, which is spurious. So in that sense, it is a gauge. It does not have any information about physics, because I keep the space-time metric the same, but the conformal metric changes just because of I chosen to do conformal completion. And what we're seeing up here is really under that what is happening. And then the statement is that these two modes are gauge invariant. They don't change anything. Okay, and the way that I'm doing it this way is also, I think, appropriate, because making the contact with linearized theory then opens door to cosmology, because that's how the cosmological perturbations are done. So that's why I'm doing it in this particular way. Okay, and this is the question that you had asked some time ago about what is the relation with cosmology, and we're going to see today and next time what the relation is. All right, so these are the two radiative modes. Now, just having said that those are the two radiative modes, what is it that I can do with them? So the first thing is the following, that we would like to have somehow tie them down more directly with something, with some geometry. This is already a geometrical quantity, but with the geometrical quantities that we are familiar with, like the Newman-Penrose tetrads and so on, that we have done so far. So let us try to do that. Today I'm going to put the homework on the first homework on gravitational waves, and also perhaps second. There will be 2 homeworks on gravitational waves, and the first one will be due a week from today, on the next Wednesday. Also, I should just remind everybody that they should be thinking about possible projects for term papers. The term papers are short, between 5 and 10 pages, not much longer. But if you think about them, they will be due at the end of the month when our semester is officially over. And I'll arrange presentations, short presentations on those topics the first week, which is the exam week. So we'll meet together and do some short presentations. We'll choose a time by mutual convenience. And finally, on the administrative matters, as you all know that I'm going to make up the class that we missed last Wednesday. I'm going to make it up next Friday. Next Friday we don't have a regular seminar here, so we can meet. I can make up that class. Okay, so now let's continue about these radiative modes. So let us suppose that I got scribe. This is 2 cross R, scribe given to me. Now I got MA. And as we saw before, what I can do is I can choose a cross section. Let me call it C1, C2. And once I choose a cross section, I acquire, I've chosen this C1, I acquire the null normal and LA to it, such that if I take this cross section, and if I take a vector which is, let me call it T under bar A, which is tangential to this cross section, then this will be 0. So this is the other normal, and of course it is always going to be the case that, So this is this is a vector which is actually tangential to this cross section. So L refers to a cross section. I don't have a canonical L. I have a canonical N, contravariant N that is given to me, but I don't have a canonical L. You choose a cross section, I get L. We saw this before when we looked at the Newman-Penrose framework. All right. Then what I said before was that, well, we can just parallel transport LB equal to 0, and then when I do that, I get L everywhere, and I can also look at affine parameter of n vector field, and these vector field with these cross sections C1, C2, C3, etc. will all be related. This will be U equal to U1, U equal to U2, U equal to U3. These are the affine parameter is going to be this constant along this. So if you give me a cross section, then using the vector field n that we got, the structure we got, we can introduce, as we saw before, we can introduce a null coordinate a coordinate U, which is the affine parameter of this vector field n up here, and U equal to constant will give me these preferred cross sections, to which this vector field L, or the covector field L, is going to be transverse, and the covector field L is just parallel propagated by L by the vector field n everywhere. Okay, so we got these equations. So now, what we saw before was a point. So in particular, it is true that because of this, it is true that LA and A, we just chose it to be equal to say -1. I just chose LA and A to be equal to -1, and then I propagated, and then I will get that. So this is what we had done when we had constructed the Newman-Penrose tetrads everywhere. So this means that LA, this LA, which is transverse to a cross section, a covector which is transverse to a cross section, can serve as our L, which really determines the derivative operator. So recall that the derivative operator is completely specified by giving DALB, because LA and A equal to -1 is nowhere vanishing, And therefore, once I know its action on L, then I know its action on everything else, because its action on the vectors which are tangential to the cross sections up here is universal. It's just the action of a two-sphere derivative operator. So we get here dA and B. There's no problem with that. I mean, but that once I know the L, I can just calculate the dA and B, and that completely determines the derivative operator. And what this sigma does for us, this sigma that we talked about does for us, is the following: that I can just take the trace-free part of this L, I can just take the trace-free part of this L, and that can be identified with the sigma AB. Now you might say, why is this the case? I mean, this is some tensor, and that tensor can be identified with sigma AB. Over here, what sigma AB was the difference between two physical derivative operators. Here it looks like I only have the one physical derivative operator D up here. So what is happening up here? Well, what is happening is that given D, given L, you can always define a fiducial derivative operator D naught such that D naught and B, this determines what D naught is completely, and this is just equal to 0. So I can define, so to say, a derivative operator which curvature is trivial by making D naught and B equal to 0. Since specifying the action of the derivative operator on L determines the derivative operator completely, if I just tell you that this is equal to 0, then I get a particular derivative operator. This derivative operator will have trivial curvature. And we're going to say a little bit more about this at the moment. It's sort of more as obvious that the curvature is going to be trivial up here. So this, if you like, is a fiducial derivative operator. And then the sigma AB that I've defined up here, I can take it to be, so I can first now take dA minus D naught A LB. This, of course, is going to be equal to sigma AB, big sigma AB, times, given any two derivative operators, the difference is big sigma AB times NC and B. And this is just equal to -1, therefore this is just equal to minus sigma AB. The difference between these two derivative operators is just minus sigma AB up here. And now, oh, so yeah, I should have. Okay. I made a mistake here. Namely, sigma AB is, I just told you the DALB, and you can calculate the shear of this L vector field, which is really taking this derivative and removing the trace up here. But there is minus sign that I missed. So it's minus sigma AB, or so if you like, sigma AB is equal to minus on the right hand side, whichever you would prefer, is equal to minus. Oh, so sigma AB I told you about it there, it's minus obviously. So we say dA minus D naught AB is equal to capital sigma AB, but this of course is the same as DALB, right? Because D naught ALB by definition is equal to 0. So the statement is that if you give me a cross section and then I just define the co-vector fields LA everywhere up here by just dragging, parallel transporting them along L, I get a whole bunch of cross sections. And the statement is that given this bunch of cross sections, we acquire kind of a fiducial derivative operator very trivially by just setting that D naught A just kills this L. Every derivative operator is specified by its action on L, and I just say that let's take the simplest case, let it kill it. Then I get a fiducial derivative operator. This fiducial derivative operator is tied to the choice of my cross sections, or the choice of the initial cross sections, because subsequent ones are completely determined. And then the statement is that the dA, and then therefore, since this is equal to this, it follows that the trace-free part of this quantity is equal to the trace-free part of this, which is sigma. Okay, let me summarize once again, and please ask questions, because people look a little bit puzzled, so please ask questions if you have. Yeah?
There's a couple of indices there, so.
Yes, this is
And C,
Thank you.
and there is C and D, right, also, there's for sigma. The
Yeah. Thank you. Thank you very much for these corrections. That's correct. This should be CD. So there was some other question. Okay. So what I'm saying is the following: that what we saw here was, without just take a scry, look at all possible space-time, look at the derivative operators, we acquire them, and we see that two derivative operators are equivalent if in fact the difference is given by sigma, which is pure trace. Therefore, the gauge invariant part is the trace-free part of the sigma. That's what we saw. Second thing I say is that, well, supposing you give me a scry and I choose a cross-section. Given this cross-section, and there is always a normal L to this cross-section that I get. Because this is a three-dimensional manifold, you give me a cross-section up here, and this L up here, given any submanifold, I always have covariant normal. So we just choose the covariant normal, and we choose the normalization of the covariant normal so that LA is equal to -1. And then the statement is that when you do that, what you'll obtain is really a family of cross-sections which are sort of parallel transported by the vector field NA, and the affine parameter U is equal to constant up here. So you get a nice slicing or foliation of scry by U equal to constant surfaces. And given every of these surfaces, I got a vector L, a covector L, which is normal to it. And if I take the shear of this covector, because this quantity taking the derivative and then removing its trace, that is the shear. So the shear of this vector field can be reinterpreted as saying that it is the difference between the given physical derivative operator and a trivial derivative operator, where the trivial derivative operator is constructed using this specification of cross-section. So given L, I get a bunch of cross-sections, and then I'm taking sigma, taking the shear of this. Maybe I should use some other notation here. Let me call it sigma up here, which is bold-face sigma. The bold-face sigma is a shear, and what we are seeing here is that this bold-face sigma, the trace-free part of this, so the trace-free part of sigma AB is what I call sigma there. And this equation says that the geometrical shear of this L is the same as the trace-free part of this big sigma, where the big sigma is the difference between these two derivative operators. And so often this sigma is called the shear, asymptotic shear. So again, the waveforms, if you like, are really coded in this asymptotic shear. Now, because of the properties of the sigma, which is that it is symmetric, transverse, and traceless, sigma is so. From now on, I'm dropping the distinction between the bold-faced one and this one because they're equal to each other. So I'm dropping this distinction. So sigma AB times NB equal symmetric, transverse, and traceless. So because of these properties, it follows immediately that if I were to use this Newman-Penrose terminal tetrads, so that I choose here Mn and bar as being the vectors which are tangential. This is the tetrad that were constructed a while ago while talking about various components of the wide curvature. Then it follows that I can expand out sigma and b in terms of m and m bar. So first of all, it will have no L component because it is really transverse and traceless. So therefore, this can be expanded just as some quantity times MA, and for some reason one puts a bar and minus. That's convention in the literature. Sigma bar naught times MA and B plus sigma naught times M bar A. So the only other terms could have been MA M bar B, but this is pure trace, and I don't have trace up here, so because of this condition, there is no term like that. And because it is transverse, I cannot have terms of the type MA L B or M bar A L B. I cannot have terms like that because then if I transvect with N, it will hit L and I need a non-zero answer. I need to get 0. So this is the condition because this is the trace-free condition tells me that this is 0, and I don't have terms like that because of transversality. So if you like this sigma ID, you can think of as being living on this cross section, just on the intrinsic cross section up here, and it can be expanded out in this particular way. Okay. And therefore, this is often called, this sigma naught is often called shear. So shear function. So shear, but this is a spin weighted function. We can spin weight because of this m bar. This has no spin weight. This has spin weight -2. Therefore, this has spin weight 2. So this shear function with spin weight 2. And in the literature, you will always often find the sigma naught. And then in the waveforms that you get in LIGO, what one is plotting is a real and imaginary part of the sigma naught. That's what is being plotted in the left line. So this is the spin 2 part of the waveform. There's a real and imaginary part of the sigma naught. Okay. So the next thing that we should do is understand. So what we have seen so far is that we got these derivative operators, and morally it is these derivative operators, or if you like, the gauge invariant part of these derivative operators, that capture the radiative modes. But now we would like to understand better the interplay between geometry and physics. Because on the geometrical side, if you give me a derivative operator, the first thing anybody would do is to commute the derivative operators and calculate the curvature tensor. And then on the physics side, we would like to know what is the relation between the curvature tensor of these derivative operators and the observable physical quantities. So I'm not doing it logically. I'm just giving because of efficiency. I'm sort of say mathematically. I've told you what the derivative operators are, and if you like, I just whisper in your ears that this is the information about the radiative modes. And then we're going along, and we're going to get more and more reason why these are the two radiative modes, if you like. So just keep this in mind, and at the end of the day, if you like, you can say logically why these were the two radiative modes. At the moment, I'm just going back and forth between physics and mathematics. Mathematics, I'm doing systematically. Physical things, I'm just telling you ahead of time what the interpretation is. Okay, so now we get this Now, the next thing that we would like to do is to calculate the curvature. What information does this curvature have? Of course, ultimately what we want is to calculate the curvature of the equivalence class of D. But to begin with, let's calculate the curvature of D, which means that there will be some part of the curvature which will be invariant under this conformal freedom, and that is the one which has physical meaning. The rest doesn't have physical meaning. So curvature. So we just take 2 times dA dB times alpha c, and this will be equal to the Riemann tensor. Now we expanded on this in 4 dimensions several times in terms of the wild part and the Ricci part. But in 3 dimensions, just the symmetries of the wild tensor tell you that there is no wild tensor. And that is the reason why in if I were space-time were 3-dimensional, then there are no gravitational waves. Gravitational waves come into existence only in 4 dimensions and higher. So here, of course, we are in 4 space-time dimensions, but Scri is 3-dimensional. And so mathematically, the curvature tensor, the Riemann tensor up here, can be expanded out just using, there is no wild part to this curvature tensor, so we can just expand it out, and that is, I just want to get the sign right. Okay, I wrote it down somewhere. Yes, I did. So this can be expanded out as QAC. This is all on Scri. I'm not putting hats everywhere because everything is on Scri. So every equation should have hat. So the Riemann tensor is just determined by this S tensor. There is no, in the 4 dimensions there will be plus the wild tensor term, and we don't have that wild tensor terms. And this S tensor, SAB up here. Okay. And then I got two tensors up here. Let's say one is SAD with one down, one up index structure. And this is this is really the curvature information up here. And then I got with these indices up here. And this is just obtained, as you might imagine, SAC is just equal to SCD, SCD. So I'm lowering the index with this metric, degenerate metric Q. Because the metric has signature plus plus plus, it's not a non-degenerate metric. Therefore, some information is lost in lowering the index up here. So if you like, the full information about the curvature is in the second rank tensor with one up and one down in this index. However, in the full formula, I also have SCA, where it's both downstairs indices, and this tensor has slightly less information than this tensor. So just keep this in mind, and then we proceed up here. And now the statement is that I can take this SCA downstairs tensor, and I can extract gauge invariant part of it, or conformal invariant part of it. Now, how do we do this? The simplest way, I'm just stating you facts, and there are calculations which will justify this fact, but those are reasonably long calculations. That conformal invariant part can be obtained as follows. Go to a body frame that fixes the conformal factor almost all completely. Go to a body frame. You're only given a 3-parameter family of freedom, body conformal frame. So the metric is that of a round metric. So that QAB is a unit two-sphere metric. And in that frame, you just take the trace part. It's somewhat not so surprising because we saw here the trace part is always has gauge information, and it's true here too, that what I do is I just subtract the gauge part. So this SCA, by definition, has a property that if I put n into it, I will get 0. And so I take here SCA minus 1/2 times QM and SMN times QC. Just take the trace free part of this S in the body conformal frame, and the statement is that this is conformal invariant. So if in fact Hongchow chooses to use one boundary frame up here, and Song uses to choose another boundary frame, there are 3-parameter family of them, and they calculate this quantity will not change. This quantity is conformally invariant. I'm just stating this, but it is a straightforward calculation to check that this is the case by making conformal transformations explicitly. And so the statement is that SAD minus 1/2 SMN QAB. This is conformally invariant. I'm in the boundary frame, and therefore it just remove the trace. There's also a procedure to do it in a general conformal frame, but it's much more complicated to write out the formula. It's much larger. Yeah.
Is it obvious that the, I guess maybe I missed something, S dot n is 0?
Yeah. So, because you're right. So, the point is that this S up here, this is a tensor. I should have written down all these properties. I did not. SAB has a property that SAB and B is equal to some function times n. So NA is equal to some function times NB. This S has this property, and therefore when I lower the index with one index, then the statement is that, and therefore the statement. So SAB and B will be 0 because of that. There's a property for this thing. And so it's not, I mean, you have to play around a little bit. It's not pretty profound. It's just ordinary differential geometry in 3 dimensions. It is some, you just have to play with the algebraic symmetry. It's not very, very deep. I'm going to give references also on the web page up here. So if I take SAB minus 1 of this thing, so this quantity is NAB, and this is called the Bondi-News tensor. So this Bondi-News tensor, we'll see why it's important in a minute. This Bondi-News tensor has information about the invariant information about the curvature of D up here. Again, this bond-induced tensor by construction is symmetric. It is again transverse. This bond-induced tensor is symmetric and transverse and stressless. Again, this symmetric transverse stressless again up here. So you might say, well, is there some relation between this sigma and the bond-induced tensor? And the answer is yes. This bond-induced tensor is just the time derivative of that sigma. In other words, an AB is just ln of sigma. I can calculate sigma in this particular way. It is really shear of these L vectors, and then the statement is I can take n, and that's just the time derivative. So if you like, sometimes people just write it as sigma dot AB. So, or sometimes people expand out NAB also as n times m bar A, m bar B, n bar times m A and B, plus n times n bar A, m bar B, and then the statement is that n dot is just n is just equal to sigma dot. Because sigma naught. For some reason, one puts a naught here, but for the bond-induced function, one does not put a naught. One could logically just put a naught if you like, just to be consistent, and then you put a naught up here, and then that is the bond. So basically, the time rate of change of the shear is the bond-induced. And we're running out of time a little bit, but let me just state the results that will make the overall structure complete. And the next time I'll begin with a grand summary, then we'll start with cosmology. So, now we got this bond-induced tensor. And now finally, well, two points. The first point is that we can now ask for properties of gravitational waves, physical properties of gravitational waves. And this again is a beautiful interplay between physics and geometry. We'll see that the energy carried by the gravitational waves, the momentum carried by gravitational waves, is completely determined by this News tensor. In the old literature with Bondi and even with Penrose and Newman and various things, people always dealt with n and with sigma, these spin-weighted functions up here, and this was called the News function. But in fact, this News function geometrically is not a function. News is a tensor. And furthermore, this tensor is really a curvature tensor. So this was something that I found much later, in the 80s, that in fact there's a very geometrical, nice interpretation of the Bondi News that it really is a tensor of the intrinsic derivative operator on scri, and the properties of the following. Then supposing we want to find out how much energy is carried and how much momentum is carried by gravitational waves. Now notice that we don't have a really stationary tensor for gravitational waves. So how are we going to calculate it? So we had two problems when we transited from electrodynamics to gravity. The first problem was that we didn't have any symmetries. Energy is a generator of time translations, momentum is a generator of space translations. We now have actually resolved that because at scri, we do know what time translation means and space translation means, or we know what translations mean, if you like. And in any given Bondi frame, the time translation is just the vector field NA, and the space translation are the first three YLMs. Space translations are alpha times NA, where in the Bondi frame, alpha will just be equal to cos theta for the z directional translation, and will be equal to sine theta sine phi for the y directional translation. These are just the projections of the vector r along the z-axis, can be unit vector, the r cos theta. So if it's unit, then it's a cos theta. This is a projection on the y-axis, and this will be the projection along x-axis. I explained to you this last time that the translations, the BMS group admits a four-dimensional translation subgroup, And one way to characterize is to go to the body frame and just look at the first 4 YLMs. Of course, if you are in Minkowski space, in the Minkowski space, you do know what translations are. And if you look at them at infinity and use a conformal completion in the body frame, then these are exactly the vectors that we obtain. They're all parallel to n, but this is, so to say, pure time translation in that particular body frame. And then this is really a z directional translation, y directional translation, and x directional translation. So we know what the translations are. So we are asking, what are the generators of these space-time translations? We don't have stress unit answer. But what we can do is we can construct, we're not going to do it in class, but I'll just state it. We can construct a symplectic space or a phase space of radiative modes from scratch, so to say, from first principles, because we know that the space of solutions to Einstein's equations has the structure of a phase space called covariant phase space, and we can express the symplectic structure in terms of the fields on scratch, and therefore we get a phase space of radiative modes. It's again a very nice geometric construction, and the statement is that we can ask, what does BMS group do? Well, it generates canonical transformations, it preserves the symplectic structure, it preserves the Poisson bracket. For mathematics literature, we have a nice momentum map from the BMS group into, from the phase space into the dual of the BMS group, if you like. So these are we can ask for the canonical transformations, and then therefore we can ask for the Hamiltonians, which generate the BMS transformations. And in particular, we can do it for translations and for space translation, time translations and space translations. And what we find is that, in fact, the generator of the time translation is just, so these give us fluxes. Yeah, we just have 2 minutes, so let's stop. These provide fluxes of. So supposing you give me a portion of scribe, I should just write up here. Supposing you give me a portion of scribe, you can even give me as a cross section. Supposing you give a portion of scribe like that, bounded by cross section C1 and C2. Let's call it delta scribe. And I would like to know how much gravitational energy is, how much energy is carried by gravitational waves through this little region of scribe here. You know, for some finite amount of time and in all angles, how much energy is emitted by gravitational waves. And the formula we obtain is that the energy through this delta scribe is just integral of NAB squared and this is the volume element of scribe, so this is du times sine theta d theta d phi or delta scribe, or if you like, this is just equal to the news tensor that is given up here, like you put naught here, square times d3 square. And the momentum in the alpha direction, or in the I direction if you like, alpha I, alpha 1 is this, alpha 2 is this, alpha 3 is this. Let's call it alpha I. So this momentum through delta scribe is just given by alpha I. So there is very beautiful interplay between geometry and physics. Geometry tells us that we should be looking at curvature tensor of these D's, and indeed you do that. And you look at the conformally invariant part, and that is in the body news up here. And the statement is that when you construct the Hamiltonian framework to calculate the formula for energy and momentum, they are just given by the square of the news tensor and square of the news tensor weighted by the first 3 spherical harmonics. So that's what we get. Okay. So basically that is where we are. That is why there is a beautiful interplay between geometry and physics. The only thing that is left from full general relativity point of view is to relate this to the radiation field at sky in terms of the Wild tensor that we saw before. And again, we'll see that can be constructed completely from the curvature tensor up here. So the universal structure is common to all space-time. The derivative operators vary from one space-time to another. And the derivative operators carry the information about the gravitational waves. There are two radiative modes. From one space-time to another, I'll get different derivative operators. How many different derivative operators can I get? Well, as many as there are these sigmas. And these sigmas have information, interpretation of shear if you introduce a cross-section, and then the construction gives you a whole bunch of family of cross-sections. The shear of this cross-section is what is containing the information about radiative modes. In stationary spacetimes, you can always find cross-sections such that the shear is 0. So your derivative operator, if you like, is just a trivial derivative operator up here. But in general, that's not the case. And then the energy carried is completely given by square of the curvature of D using square of the conformal invariant part of the curvature of this derivative operator. So it's very, very nice geometric framework. If you have questions, please stop by the office hours about today or on Friday. And again, today there will be a homework on it will be shorter than the previous homeworks because there are two homeworks. The first one will be due a week from today. The second one will be due 2 weeks from today.